So today we're going to have a look at electromagnetic induction. Now a big part of this firstly is magnetic flux. What magnetic flux is, it's the product. So if we need to multiply the magnetic field strength through a certain area. Okay, so flux just means how much of something is passing through a certain area. And if we're talking about magnetic flux, it's just the area times by the magnetic field strength. So you can see here we have a yellow square just over here. We've got a yellow square, we've got some magnetic field going through it. Now whatever that area of the square is times by our magnetic field strength will give us our flux. Now this is the symbol and our equation. So the unit for magnetic flux is WB. Now you'll hear it pronounced Weber, but it's actually pronounced Weber. But either way, WB is the symbol for that. Okay, and this symbol here for magnetic flux is phi, PHI, the Greek symbol for phi. So what is electromagnetic induction? Well, it's the process in which changing magnetic flux induces a potential difference in a conductor. Okay, and that potential difference is referred to as EMF, or the electromotive force. So what you can see here, we've got a magnet north and south. We've got a magnetic field going through that. Now, if that's changing that magnetic field, it induces a potential difference. Okay, and we can make electricity. Now, we call this an EMF, electromotive force, and this is how we create electricity. So let's have a closer look at that. What we've got here is a magnetic field and some loops of wire. So what we can do is, if we change the magnetic flux, so the amount of magnetic field through the wire, we can either do that by moving, as you can see, we're moving the magnet closer here, or you could change the magnetic field strength. What happens here is we create a current, and you can see down here in our galvanometer, we're creating a current, okay? And this is the exact opposite of when we had a current going through a wire, we created a magnetic field. Now, if we put a magnetic field through the wire, we create a current. So it's the exact opposite of that. All right, so from here we get two laws that are really important. The first one is Faraday's law, and what the Faraday's law says is that the induced EMF is equal to the rate of change of magnetic flux. Now what that means is the potential difference, and hence the current that we pick up in this, is equal to the how much we're changing this magnetic field moving through our loops here. Okay, and Lenz's law is the second one, and what Lenz's law states is that the induced EMF, so the EMF that causes this current, creates a current in the direction that opposes the magnetic flux. Okay, so what we do is the current that we make, it spins in a certain direction so that the magnetic field, using our right-hand curl rule, opposes. So it comes in this way, and it goes in the opposite of our little blue lines here. Okay, so that's Lenz's law and Faraday's law. Now we get a really important equation here. You can see what we have is the EMF is equal to the change in our value phi. Now we just saw phi here. All right, that's the magnetic flux. All right, so the change in the flux and the time that took, okay, that equals our EMF, and we can use that to work out our current. Now we're going to skip to a really important rule, and it may be even more important than the previous one. So that only works for one loop, but you can see here we've got 1, 2, 3, 4, 5, 6 loops around here. So we can actually write the EMF equals the number of loops times the change in our magnetic flux over how long it takes. Okay, so this is just a little bit different with the number of loops. So Lenz's law also obeys the conservation of energy, and this is a really important little concept. Now, when we're doing this, when we're moving our magnet back and forward, we're creating a current in this bottom wire here. So what the conservation of energy says is you can't create or destroy energy. So as we're moving this forward, we're creating energy. So we need to lose it somewhere. And the way we lose it is when we're moving this magnet, north-south magnet towards and away, the magnetic field created by our wires opposes that. So you can actually feel, if we're moving it towards, you can feel it will be pushing the opposite way. Okay, and same as when it goes back, so you'll feel some kind of repulsive force in both directions. Okay, that tries to negate where you're moving. Because we're creating energy, you've got to lose it somewhere, and it comes in the fact that we lose that push energy. Okay, and the last thing we have to look at is these little eddy currents. Okay, I really like their name. What we have with eddy currents is if we have a magnetic field, okay, you can see here with the green line, it's a magnetic field, and it's going through a piece of metal that's moving. So this, you can see this is rotating around. What happens is the magnetic field wants to oppose that magnetic field you can see from this magnet. So the way it does that is it creates these eddy currents, these circular currents, and what we get is we create these little blue magnetic fields. So if we circle around, we use that right-hand rule, the circles are going this way, okay, we get magnetic field in the opposite direction. All right, so these eddy currents, these circular currents, are created to oppose the magnetic field that is on a piece of metal. Okay, thank you.